Now we need to investigate the order of integration for triple integrals and what the average value of a function means when I'm working with triple integrals. The order of integration does make a difference, and we saw this with double integrals. Changing the order of integration with double integrals could make my life easier, and it could take me from something I couldn't even evaluate to something that I could. The same thing is true for triple integrals. But there are a lot more ways to interchange integrals when I have a triple integral, and this means there's more ways to make things more complicated. And there's no hard fast rules here for what we want to do, and you may need to engage in a little bit of trial and error to make sure that you're working efficiently. It's a good idea to look for ways that order of integration helps reduce the number and complexity of the variables in the integrand with each iteration of integration that I do. With each ordering of integration, I need to also reevaluate the projections onto the coordinate planes in order to determine the correct limits of integration. So let's work an example where I need to change the order of integration as indicated and then evaluate the integral. I'm given the integral from 0 to 5 of the integral from -1 to 0 of the integral from 0 to 4x plus 4 of dy, dx, dz. But I want to integrate this in the order dz, dx, dy. I'm going to use the limits of integration I was given in the original to construct the boundaries for my volume. I'd simply plot the planes given by each limit of integration, and I get a triangular shaped prism. This prism lies in the second octant, and it has a triangular cross section in the xy plane. It is bounded on the top by the plane z is equal to 5 and the bottom by the xy plane. The plane y is equal to 4x plus 4 is the bound on the slanted edge of my prism, and the edge that lies in the xz plane is bounded by a rectangle, with one side aligned between -1 and 0 on the x-axis and the other aligned between 0 and 5 on the z-axis. If we change the order of integration so that I integrate with respect to z first, I still have to move from 0 to 5 in z. In the x direction, I'm going to move from the plane y is equal to 4x plus 4 to 0, which gives me x is equal to y minus 4 over 4 to x is equal to 0. And finally, I have to move from 0 to 4 in the y direction, so that my integration with this new order becomes the integral from 0 to 4 of the integral from 0 to 5 dz, dx, dy. Now I want to evaluate this integral. My inner integral from 0 to 5 dz becomes z evaluated between 0 and 5, which just gives me 5. I plug that into my middle integral, the integral from y minus 4 over 4 to 0 of 5 dx, which gives me 5x evaluated from y minus 4 over 4 to 0, and it gives me -5 times y minus 4 over 4, which I can rewrite as 5 minus 5y over 4. This becomes the integrand in my outer integral, and I get the integral from 0 to 4 of the quantity 5 minus 5y over 4 dy. This integrates to 5y minus 5y squared over 8, evaluated between 0 and 4. I plug in those limits of integration and I get 20 minus 10, or 10. Now I want to talk about average value in triple integrals. The average value of a function in one variable was arrived at by taking the integral of my function over an interval I and then dividing that by the length of my interval. The average value of a function in two variables over a region R was given by integrating the function and then dividing by the area of the region R. So, any guesses on how to find the average value of a function in three variables? Pause the video and think about it for just a couple seconds, and then restart the video to check whether or not you're on the right track. It shouldn't be a surprise that the average value of a function in 3 variables over a region D will be given by integrating the function and then dividing by the volume of the region. So if f is continuous on a region D in R3, then the average value of f over D is going to be given by the average value of f is equal to 1 over the volume of the region D times the triple integral over the region D of f of xyz dv. Let's put this into practice. I'm going to find the average value of the squared distance between the z-axis and the points on the conical region D given by the set of all points x, y, z, such that 2 times the square root of x squared plus y squared is less than or equal to z, which is less than or equal to 8. I'm going to sketch my conical region here because it helps me visualize what's happening with my integration. This is a volume of a cone that is oriented so that its peak is at the origin and its base is at the height of z is equal to 8. Now, the volume of a cone in the geometry we've studied is given by the formula 1/3 pi r squared times z. The projection onto the xy plane is a circle of radius 4. So that our volume here is 128/3 times pi. In the xy plane, my region of integration will take x from -4 to 4, and y is going to go from negative square root of 16 minus x squared to square root of 16 minus x squared. The square of the distance between the z-axis and points in the conical region will be given by x squared plus y squared. This is the function I want to integrate. So if my volume is 128 over 3 times pi, 1 over my volume becomes 3 over 128 pi, and I have that multiplying the integral from -4 to 4 of the integral from negative square root of 16 minus x squared to square root of 16 minus x squared of the integral from 2 times the square root of x squared plus y squared to 8 of the quantity x squared plus y squared dz, dy, dx. My innermost integral gives me an integral from 2 times square root of x squared plus y squared to 8 of x squared plus y squared dz. This is equal to x squared plus y squared times z, evaluated from 2 times the square root of x squared plus y squared to 8. This gives me x squared plus y squared times 8 minus the quantity x squared plus y squared times 2 times the square root of x squared plus y squared. I'm going to rewrite this a little bit. I'm going to write it as 8 times the quantity x squared plus y squared minus 2 times the quantity x squared plus y squared raised to the 3/2 power. This becomes the integrand in my middle integral. So I get 3 over 128 pi times the integral from -4 to 4 of the integral from negative square root of 16 minus x squared to square root of 16 minus x squared of the quantity 8 times the quantity x squared plus y squared minus 2 times the quantity x squared plus y squared to the 3/2 dy dx. The remaining 2 integrations can be greatly simplified if I convert to polar coordinates at this point. This becomes 3 over 128 pi times the integral from 0 to 2 pi of the integral from 0 to 4 of the quantity 8r squared minus 2r cubed r dr d theta. This gives me 3 over 128 pi times the integral from 0 to 2 pi of 512 minus 2048 over 5 d theta. I get 12 over 5 pi times the integral from 0 to 2 pi of 1 d theta, which gives me 12 over 5 pi times 2 pi, or 24 over 5. So now you get to try it. Pause the video and find the average value of f of xyz is equal to 6xyz over the points inside the hemisphere of radius 4 centered at the origin with its base in the xy plane. When you're ready, restart the video to check your understanding. The first thing I need to do is determine what my volume is going to be for my region. The volume of the hemisphere is given by the formula 1/2 times 4/3 pi r cubed. This is just 1/2 times the volume of a sphere. If you feel particularly adventurous, you can always try and derive this formula for volume using triple integrals. The equation for a hemisphere centered at the origin with a radius of 4 is given by x squared plus y squared plus z squared is equal to 16. In the xy plane, my region of integration takes x from -4 to 4 because the projection is a circle in the xy plane. My y goes from negative square root of 16 minus x squared to square root of 16 minus x squared, and z is going to go from 0 to the top of the curve of the hemisphere, which is the square root of 16 minus x squared minus y squared. I use this to set up my iterated integral. I get 9 over 64 pi times the integral from -4 to 4 of the integral from negative square root of 16 minus x squared to the square root of 16 minus x squared of the integral from 0 to the square root of 16 minus x squared minus y squared of xyz dz dy dx. My innermost integral is the integral from 0 to the square root of 16 minus x squared minus y squared of xyz dz, which is equal to 1/2 xyz squared evaluated from 0 to the square root of 16 minus x squared minus y squared. This gives me 1/2 times xy times the quantity 16 minus x squared minus y squared. I'm going to distribute 1/2 xy into the parentheses, and I get 8xy minus 1/2 x cubed y minus 1/2 xy cubed. This becomes the integrand in my middle integral. The integral from negative square root of 16 minus x squared to square root of 16 minus x squared of the quantity 8xy minus 1/2 x cubed y minus 1/2 xy cubed dy. This gives me 4xy squared minus 1/4 x cubed y squared minus 1/8 xy to the fourth evaluated between negative square root of 16 minus x squared to square root of 16 minus x squared. I plug in those limits of integration, and I get two identical terms that are subtracted from each other, which gives me a net of 0. Because this middle integral has gone to 0 already, my average value is going to be 0, and I'm done. This is how I can use my triple integrals to find the average value when I'm working with volumes. Be sure and let me know if you have any questions.